Okay, welcome to calculus. Let's get going. The first thing we need to do is establish some new tools um, because stuff doesn't always work out nice and neat, and we need to be able to dig in to the functions and the graphs and analyze what's going on. Okay, so I'm going to be talking a lot about the behavior of the x value and the behavior of the y value. And hopefully I'll be able to demonstrate that graphically. So for now, let's consider this function right here. Now, if you try to plug in a 1, you see that 1 squared minus 1 gives you a 0. Let me write this down here. If you plug in the 1 here, you're going to get a 0 here and a 0 here, right? Well, 0 over 0 doesn't exist. And you'll notice that I always write D and E for does not exist. Not only does it not exist, it's indeterminate. We'll talk about that more as we move on. So obviously you can't just plug in x equals 1 into this function, because not only do you get something that's undefined, you get something that isn't even determinant. So we have to do something else. So let's examine this particular function. If you take this guy right here and you factor it, you see that you can cancel, right? So once you cancel, you're left with this simple function right here. Now, if you plug the 1 into this, you can do that, right? You get a value, you get 2. The 2 exists. So we need a tool that's going to allow us to do this process right here so that we can examine the behavior of this function as x approaches that particular value. So our new tool is something called a limit, all right? This new tool is going to show that as x approaches, because x can't equal 1, but how close can it get? It can get infinitely close from either side. Can you think of two numbers that touch each other, for instance? There are no numbers that touch each other because there's an infinite number of numbers between any two numbers, right? That's why we use a line, a number line, instead of a bunch of dots, because a line is continuous everywhere, and you can't find 2 points on a line that actually touch each other because you can always go between and between and between. Isn't that awesome? That the real numbers are not just infinite on the ends from negative infinity to positive infinity, they're actually infinite inside themselves. Ooh, gives me chill bumps. So I think it's awesome. That means that we need a tool, though, that's going to show as x approaches the value of 1, what does the y value approach? And we're going to see that it approaches 2. Now, what I did up here is called a numerical limit. That's in section 3. We'll do a lot of those. But for now, we want to look at it numerically and graphically. So we'll talk about that a little bit more later. So even though you can't plug x equals 1 into the function to find the y value, because that y value doesn't exist, right? We can examine how the y value behaves as x gets infinitely close to 1. And we'll see that the y value gets infinitely close to 2. Okay, the way you write a limit, you see LIM for limit. We're saying that the variable that is independent in our function is going to approach a value. That's an arrow right there. So the limit as x approaches 1 of this function is 2. The limit as x approaches 1 of that function is 2. That's how this is read, and this is how you write it. Okay, so the graph of this function is just the graph of the simplified form x plus 1. You see this graph right here, right? It crosses the y-axis at +1. It crosses the x-axis when x is -1. Connect the dots, boom, you're done. However, the function itself still has a limit on its domain. Just because I factored and canceled doesn't mean that this function wasn't what we were concerned with, right? It still has a domain restriction. So graphing the line x plus 1 isn't the same as graphing the function x squared minus 1 over x minus 1, because there is a domain restriction where the bottom equals 0, and thus you get this open circle at x equals 1. But where does that open circle happen? It happens at y equals 2, right? So what we're going to do later is we're going to show that as the x value is coming toward +1 from the left-hand side, follow that graph, the y value is approaching 2 from below. As x approaches 1 from the right-hand side, where it's bigger and it's closing in this way, follow the graph, the y value is approaching 2 from above. So that's how you say the limit as x approaches the function, as x approaches 1 of that function, the y value will be approaching 2. You're getting the same y value coming from this direction and from this direction. So to say that again, notice that when you plugged x equals 1 into the function, you got 0 over 0, which is indeterminate. It's not even undefined. It's worse than that, right? But if you get a 0 when you plug in the value, that means x minus that value was a factor. And if you get 0 on the top and the bottom, then you had x minus 1 as a factor on both the top and the bottom. Therefore, it can be canceled. So I'll talk more about this later, but if you plug in your value that you're finding the limit of and you get 0 over 0, you know that you can factor this thing and cancel it. Sometimes that means you can get an actual value. Sometimes it doesn't, but most of the time it does, and you'll be doing that in section 3. All right? Even though canceling removes the 0 from the denominator so that you get a value that exists, the domain restriction survives the canceling, and it's still in effect because you're actually doing f of x, not the simplified version, okay? That gives you that open circle, and it's called a removable discontinuity in this case. So if you have a circle instead of an asymptote, you have a removable discontinuity, and we'll talk more about discontinuities later. Okay, again, look at the graph of this function that we had. Again, there is an open circle where x equals 1, but y is equal to 2 at that place. Now, what I want to talk about now, and it'll come up more later, is a left-hand limit and a right-hand limit. Now, your left-hand limit is if you're coming at x equals 1 from the left-hand side. So over here on the left-hand side, the x value is actually 1 minus a little bit. So you have this little superscript of a minus sign. That tells you it's a left-hand limit. You're coming from 1 minus a little bit. You plug that value in, it's going to get infinitely close to 2. Now the right-hand limit means you're coming from the right-hand side, so you're a little bit bigger than 1. You're at 1 plus something. So as x gets infinitely close to 1 from the plus side, right here, then you're still going to get 2. Now if the left-hand limit equals the right-hand limit, then the limit exists, and whatever value that was is what your limit equals. In this case, 2 equals 2, so your limit, your just straight up limit equals 2. Okay, let's look at a couple other situations here. Let's look at the function 1 over x. And we know we can't divide by 0, So x equals 0 is not in the domain of this function. So f of 0 does not exist. So we're either going to have an open hole or we're going to have an asymptote. But we know that if we're tracing this graph, we're going to have to pick up our pencil when we get to x equals 0. There is a discontinuity there because the function doesn't exist there. Okay, what happens to the y value when x approaches 0? So we need to check this from the left and right hand side. Remember, left will be less than 0, and 0 in this case, and the right will be greater than 0. So if we look at this graphically, this is what 1.2 is concerned with. You'll be looking at graphs and figuring out limits. So the x value in question is 0. That's this asymptote right here. If you can graph the thing, then you can eyeball it and see that as x approaches 0 from the left-hand side, follow the graph. What is it pointing to? It's pointing to minus infinity. If you follow it from the right-hand side, as the x value gets closer and closer to 0, follow the graph, it's pointing to positive infinity. So I can't imagine a situation where negative infinity equals positive infinity. So obviously this limit does not exist. They're pointing to different numbers. Now, numerically, and this is a pain in the neck, by the way, if we're approaching 0, this thing right here is your left-hand limit. So I get a number that's pretty close to 0 but less than 0, so it's negative. And then I get a little closer, and then I get a little closer than that. I plug those x values into 1 over x, and I chug out my y values. You see that we started at 10, then we got another 0, then we got another 0. As we get closer and closer to 0, on the negative side, we're going to get bigger and bigger negative numbers. So as we get infinitely close, we're going to get minus infinity as our value. All right? Hold the phone. Let me make this because it'll get cut off at the bottom, I think. Okay. Now, this guy is the right-hand limit. So see how the x values start close to 0, but they get closer and closer and closer, and they're coming from the positive side. So this is the right-hand limit. When I plug these values in, I get positives, whereas up here I got negatives. So you see these values are getting bigger and bigger. I'm adding a 0 every time I add a decimal place, which means I'm going to go to positive infinity on that side. Well, minus infinity doesn't equal positive infinity. So whether we're looking at the graph or we're looking at it numerically, this limit doesn't exist because the left-hand limit does not equal the right-hand limit. Okay, next, let's take the same function that we had before, but now we're looking at x squared in the denominator. So when we plug in these negative numbers that are getting closer and closer to 0, we're getting positive values, and they're growing really super fast. So it's easy to see that from the left-hand side, as x gets closer and closer to 0, y is getting infinitely large. And from the right-hand side, we're going to get the same values. So it's growing really fast, and as we approach from the positive side, getting closer and closer to 0, the y value is blowing up to infinity. These two guys are the same number, only are they? Do you ever really get there? No, not really. And if you look at the graph, you get this right here. This is going to, at 1 you get 1, but at 1/2 you're going to get up here at 4. It's steeper than what I drew it. At 1/3 you're up at 9. At 1/4 you're up at 16. So it's growing really, really, really fast, and both sides are positive. Now, the book says that, let me write it down here, that the limit as x approaches 0 of 1 over x squared does not exist. All right? Now, that's fine because you're never going to get where you're going, right? There is no number that y is approaching as it gets to as it gets closer to 0, because it's blowing up without bound, right? Growing like crazy. However, that doesn't give you a whole lot of information. Larson's book says it does not exist. Some books would say that it diverges, which means it just blows up. But I will accept that the limit as x approaches 0, just between you and me here, goes to infinity. It's never going to get there, but saying this right here shows that no matter which direction you're coming from, you're going to the same place, and something equaling infinity isn't quite right. It's not necessarily correct, but it does approach infinity. And if you looked at the beginning limit that we did as x approached 1, y approached 2, it didn't equal 2, right? It approached 2. So I think it's okay for you to say that it approaches infinity. It's not going to be a correct or incorrect issue on the test. I'm just saying that writing it this way gives us more information about the behavior of the graph. Okay? So that's my 2 cents, and now we'll get back on track and do what Mr. Larson tells us to do. Okay, behavior of a function that will cause a limit to not exist. First, if the left and right hand limit are not equal, you will have problems in the book that are piecewise. Let me write one down as an example here. If you have a function that says x plus 1 if x is less than or equal to 2, and then maybe x squared for x greater than 2. Well, you see that the only place, these are both polynomials. Polynomials are continuous everywhere. They have no discontinuities. They have no domain restrictions. But if I write a function this way, where I've taken minus infinity to plus infinity and broken it up into pieces, then what I have to do is check my left and right hand limit to see if it's continuous at the places where the domain has been taken apart, right? So let's see what's happening for this one. The limit as x, the only place where we're concerned about is x equals 2. From the left means that x is less than 2. That's this guy, which means I'm going to plug it into this function of x plus 1 is going to be 2 plus 1 is 3. You see how simple that was? I just plugged in the number. Now the right-hand limit, the limit as x approaches 2 from the bigger than 2 side, means this is greater than 2 here, 2 plus some. I'm going to plug it into this guy, and which means I'm plugging it into x squared, and I'm going to get 2 squared is 4. Well, notice that the left-hand limit doesn't equal the right-hand limit. The x approaches 2 from the minus does not equal the right-hand, the right-hand limit, x approaches 2 from the plus. Therefore, that's what the 3 dots mean. Therefore, the limit as x approaches 2 doesn't exist. And this graph right here is not a graph of this function. It's just showing this situation, right? So, hello, I have an idea. Should have thought of this in the first place. 1, 2, hold the phone. This is why I should think of things earlier. Ran out of room up there. you know what? I got an idea. Let's move this down. So 1, 2, 1, 2, 3, 4. Notice that this line right here does not equal 2. So that's an open circle at 4, and it grows that way because it's a piece of a parabola. Whereas on the other side, where x is smaller than or equal to 2, we have this. So at 2, we have the filled in circle at 3, and it's a straight line this way, slope of 1. So now your graph matches your piecewise function there. And you see that the limit doesn't exist because as I approach 2 from this side, I'm headed to 3. As I approach 2 from this side, I'm coming down and heading to 4. Well, my left and right hand fingers are not pointing to the same point on the graph, so the limit doesn't exist. All right, the second case that gives us a limit that doesn't exist is if it grows without bound, like we saw here. And I used this one because I wanted to show that it's, pointing in the same direction, but they're never going to point to the same point. So the book will say that that doesn't exist. Another case in which a limit won't exist is if it oscillates infinitely fast or an infinite number of times in between two set values, and it doesn't even have to be, it could be oscillating infinitely tall as well. Just copied this from the book. But look at this function right here. We've already shown that as x approaches 0, this thing is going to go to either negative infinity or positive infinity. And the sine function is always between plus or minus 1. So let's turn the page and see what happens. So we have a situation here where the theta is blowing up, but the sine is bounded between plus or minus 1. Okay? So as that graph, and I'm not even going to try to draw it, you can see it in the book, but as you get closer and closer to x equals 0, the sine function, you know how it has a wave up and down, it's going to start oscillating infinitely fast between the y values plus or minus 1. And as it gets closer and closer to 0, this grows faster and faster. So it's going to oscillate until it's just a great big blob of points, and it never settles down. So if you want to see the picture of that, look at figure 1.10 in your textbook, and it's in section 1.2. All right, this is a good stopping place. We're not finished with 1.2. We have some stuff left to do, which probably won't be on your test, but it's important to go over. So in the next video, we're going to do the formal definition of a limit. For now, stick with just these problems, and EOO, when you see that, it means every other odd. So you're going to do the first problem and skip the next odd, then you'll do the next odd, and you'll skip the next odd, and you'll do that until you get finished. So you're only doing every fourth problem. All right, so I think that's like 7 questions for this assignment, and I'll see you in the next video.